Hello. Hi all. Got 4 people waiting. Hoping it's all working okay. Only 4 people, that's disappointing. It's all right. I'll hopefully more people will join throughout the day or throughout the evening even. Right, so what I'm going to do is I'm going to try and be as quick as I can, guys, see if I can rattle through this in 40 minutes to an hour or so. And I will, first thing I need to do is share my screen, share, and then hopefully you guys will be able to see what I see. And then if I do view full screen, can I do that? I do view 1 page, multiple pages. No. One page. What I'll do is I'll just scroll up. Just a reminder, folks, that if you want to be able to see it properly, then it's worthwhile. If I do web layout, maybe. If you switch it on to HD, if you go on to the settings in the bottom right-hand corner of the thing, you'll be able to do quality and turn it up to the 720 HD. That way it'll come up a lot better in terms of you guys. Olivia saying actually jogging on, oh God. Unless you're actually jogging, Olivia, not impressed. By the way, are you guys able to hear me okay? Can someone lob me a thing on the chat, please, just saying that you're able to hear me? Does anyone know how I make this whole thing full screen? How do I make it go full screen? View, print layout, I don't know. Oh, that's really annoying. I'll go through question by question. Okay. Right. Section A, question 1. The Avogadro's constant is equal to. So this was a case of recognizing that it says atoms, Avogadro is equal to, atoms in 1 mole of any element. That can't be true because some elements are diatomic. But then it says atoms in 1 mole of monatomic. That's the right answer. If you go for atoms in 1 mole of any compound, you're going to have 1 mole. A compound has to have at least a minimum of 2 different elements. So you're going to have more than that number of Avogadro multiplied by the number of elements in it, or the number of atoms in it. Ions in 1 mole of an ionic compound. Ionic compounds have got cations and anions. So the answer is B, monatomic. Most people did well on that one. So happy with it. See if I can make this bigger. There we go. When ethene reacts with chlorine, a mixture of products formed. Which product is best evidence of free radical mechanisms? We know that free radical mechanisms, their biggest problem for FRS is that you get alternative products. Now, if you look at HCl as an example, HCl, of course, it isn't a sign because you can get lots of reactions that will. That's dead. Yeah, it's dead. Lots of reactions will produce HCl, whereas because we've got chlorine and ethane, to get butane from that reaction suggests that you must have had other steps where you formed free radicals, which would be an ethane free radical. And that would be where 2 ethane free radicals would bump together to form butane. So it was B. Next one, the naming, this was really mean because you had to run heavy light on this, folks. In terms of the double bond, you can see that I'm trying to highlight the double bond with my mouse. That in the top left corner is a methyl group, and on the right-hand side is another methyl group. Lots of people then went for Z. It can't be Z because the next atom joined to the left is a carbon, ranked high priority at 12. Then that one's low with a H of 1 being a low priority. On this side, you've got 12 and 12. So then you've got to go to the next one. So that would be 12 and 1. So the one on the top right-hand side is going to be low priority. So the 2 lows are on opposite sides. So it's an E. And of course, pent 2-ene rather than 3-ene, counting from the left to make the ene as low as possible. Relatively straightforward, but required a little bit of effort. Right, this one had most people fooled. It's 4. The reason being is if you look at the molecular formula C3H5Cl, that means there must be a double bond. And if there's a double bond, then you have to draw it out. This is where ideally I'd love to draw it out for you folks, but I'm really sorry that I haven't. But we've got geometrical isomerism appearing here as well. We've got an EZ. So you can move the chlorine from the first, second, and third. I think that's what most people did. But what people forgot is that the double bond, if you put the chlorine on the first, then you're going to have an EZ isomer as well. So that was 4. That question 4, please star it. If you still don't understand what I'm saying there, then please come and see me about question 4 in order to fix it. 100 centimeters cubed of methane gas is completely burnt in 400 centimeters cubed of oxygen. What is the final volume of the gas mix when all volumes are measured? Right. So completely burnt. If you've got 100 centimeters cubed of methane, it's completely burnt. And how much of the oxygen are you going to use up? We know that volumes of gases, of any gas, are the same. So what we've got there is we've only got all volumes measured, final volume of gas mixture at the end. So what's you're going to convert it into CO2? So it's about what's being left over. So if you've got 100 centimeters cubed of methane, the number of moles of methane you can do V over 24. But the moles of those two are equal because 1 mole of any gas equals the same. So you've got 1 mole of methane and 1 mole of oxygen. Oh, no, I need to write an equation for that, folks. I should have written that out for you. Methane plus oxygen completely burnt. It's going to form CO2 and water. And of course, at room temperature and pressure, the water's going to be liquid. That's the tricky bit. So you can ignore the water from the mix, but you're going to make one mole of CO2 because it's complete. There's only 1 carbon in it. So if you're only getting 1 mole of CO2, then the volume of that's going to be, that one requires an equation, folks. Number 5, that one, please come and see me about question 5. That requires a little bit more of an explanation than that. And gas volume questions, I'm quite happy to provide you with more of those because they're hard. And they require a bit more explanation than just it's 300. I'll run that one with you in class. I'll do some gas volumes calcs. Particles, parts per million. What is the maximum volume of gaseous hydrocarbons allowed in 10 moles of exhaust gases? So we've got 200 parts per million. I hate parts per million. Molar volume 24. So in 10 moles of gas, it's 200 multiplied by 10 multiplied by, oh no, oh God, I don't know what that one is either. Got stuck on 2 questions already just because that one needs an equation and question 6 requires you to know your parts per million. What is the maximum volume of gaseous hydrocarbons allowed in 10 moles of exhaust?
Olivia loves ppm, my favourite calculation.
I hate parts per million, Olivia. 48 centimeters cubed parts per million. I'm going to have to come back to that one, folks. My brain's not working this evening. I'll come to number, I'll do, so please flag them for me, please. 4, 5, and 6 all need more explanations. Statement, best evidence for existence of ions. Solid sodium chloride, it doesn't conduct electricity. When the electric current is passed through solution of sodium chloride. Oh yeah. So Olivia has given me the calculation 200 over 10 to the 6. She's dividing it by 1,000,000 in order to put it into particles per mole and then moles over 24,000 because it's got to be in centimeters cubed rather than dm cubed. It was a nightmare. I mean, is it short of 240,000? Because if it's in dm cubed, Olivia, then don't you have to convert to, because it asks you for centimeter cubed. Is it? Oh yeah, 24,000, you times it by 1,000. Yeah, that's fine. Over 24,000. Yeah. But you know they come up. That one's worthwhile having a look at. Anyway, let's go to the next one. Sodium chloride crystals have a regular shape. Giant covalents have a regular shape. No good. There is a good agreement between theoretical and experimental lattice energies for sodium chloride. That's the right answer. The reason being, of course, is if you've got theoretical and lattice enthalpies, lattice enthalpies apply only to ionic compounds. So if they're talking about experimental versus theoretical. They're talking about ionic compounds. Plus, if they didn't disagree, it would be covalent. We know that if it's giant covalent, then the lattice enthalpy would be enormous. This question, can I just point out, by the way, that was those last four are tricky. The parts per million just needs practice. Divide by 10 to the 6 and then x over 24, as long as you're in centimeters rather than dm over 24,000 in centimeters. Number 8, which ion has the smallest ionic radius? Right, you can rule out A and D. The reason being is they're negative. If they've become negative ions, they have swollen, increased electron-electron repulsion. The S2 minus ion will be massive. Chloride ions, that's fat. I've told you about that, fatty. Followed by and then of course the calcium 2+. The 2+ is gonna be tiny. You've taken away 2 electrons. We all know as you ionize, the ion shrinks. So the 2+ is gonna be the smallest. You'll also notice, by the way, that A, B, C, and D are also all isoelectric, which means they've all got the same electron configuration. So you're going to go for the biggest plus charge there. Which quantity is exothermic? Atomization? No. If you want to atomize something, you've got to put in energy. That's endo. First ionization energy of sulfur, you've got to rip an electron off. So that's going to take energy. The first electron affinity for sulfur. That's your answer. This is one where we discussed it in Born-Haber cycles. The second one is massively endo, but the first one is always exo. The reason being is you're adding an electron to a neutral species, so you're making a bond, mexobendo. C is going to be exothermic. All you have to do, guys, is look for which one are you making a bond. Atomizing, smashing, ionizing, ripping an electron off. Electron affinity for number 2 is massively endo because they 2 negative particles repel. So you've got to put in energy to overcome. Right, best representation for lithium iodide. So A is the right answer. You've got a distorted anion. Iodide is a beach whale of an ion. She's massive, and so it's going to be distorted by that small 1+ lithium. You can't distort positive. It was either A or C because the positive ion can't be distorted. And the negative ion, of course, C doesn't exist. You can't have C. 2 perfect ions. That's the PIM model. So watch out for that one. So it was A. Distorted anions, folks, that's what you're always looking for. Write an equation for the lattice energy. Right, if they ever say lattice energy, it means that you're making it from its ions. You always know if it's, by the way, you'll notice that the top one is the enthalpy of formation of magnesium nitride from its elements to form 1 mole. The second one has nitrogen as 2 ends. Ugh. If anyone put B, I disown you as part of my chemistry class. C, well, that's just a little bit odd. You've got 3 2+, gas. We're forming magnesium nitride gas. And if you're forming a lattice, you're forming a solid salt. So D is your right answer. It was between C and D, and you're always looking to make an ionic salt. Which pair of ions are isoelectric? Lithium is 1s2, and it's done. Oxide ion is 1s2. You could do it, good old GCSE, 2 8s.
RIP everyone who put B.
Yes, David. Anyone who put B, you're officially disowned. The answer's D. Aluminium is in period 3. You remove 3 electrons, you have the same configuration as neon. Fluorine is in period 2. It's gained an electron, having the same configuration as neon. So the answer was D for that one. Do you know what? Doing a good old GCSE 2882 on those is really, really useful for those questions. Right. Which of the following statement gives information about the thermodynamic stability of magnesium chloride? We were adopted. Were we adopted before? Yes, definitely, Olivia. So MgCl is stable with respect to chlorine and magnesium. No, it's not. Magnesium is a 1+, not stable. MgCl is unstable with respect to MgCl2 and Mg. That's kind of true, that, about the thermodynamic stability of magnesium chlorides. Oh, okay. They've then gone on to enthalpy of formations. Oh, okay. So, okay, if you have the enthalpy of formation of magnesium chloride is, so they've given us a load of true statements. Magnesium chloride is stable with respect to chlorine and magnesium. Is stable compared to them. It will still be an exothermic reaction. It just won't be very much. The formation of magnesium chloride solid is negative, so it's still exothermic. Formation, is MgCl is unstable with respect to chlorine and magnesium, which means its enthalpy is going to be positive. God, that's a really tricky question, folks. That's not easy, that. Which sign of the standard enthalpy of formations are correct? So you've got to look at the statements. And they're simply, by the way, the ones that we're comparing are the top one and the bottom one, because the one's saying stable. Oh no, stable with respect to MgCl2 and Mg. On the magnesium. You want to compare the top two, but that one says it's stable. So, yeah, you're comparing the bottom one and the top one and the bottom one. Those two statements. The first one is stable. It's going to be exothermic. Yeah. So hence a negative formation. The other one is unstable, so it's going to be positive. The second one's a complete misdirection. In the electrolysis of copper to chromate. Chromate. Guys, I did this with you in equilibrium. The dichromate is orange and the chromate is yellow. That's requiring Unit 2 knowledge in a Unit 1 paper. It's hard, that, folks. If anyone put blue or green, again, you're disowned. I'm disowning you, folks. No, that's mean, actually, because copper's blue. I'll take it back. If you've put green, you're disowned. Blue, I'll forgive you. But the answer is yellow. The positive electrode is going to attract the negative ion, which is the chromate. Oh no, Olivia, I put orange. So dumb. No, are you messing? Orange or yellow, it's not your fault. To be able to see the distinction between dichromate and chromate, that requires really good chemistry knowledge. That's tricky, Olivia. You're forgiven. Forgiven. When 10 centimeters cubed of nitric acid solution reacts with 20 centimeters cubed of sodium hydroxide, the temperature rises delta T. Repeating the reaction with 15. Aha, this is dead clever. Guys, right. Would you agree that the number of moles of whichever, these two are in perfect, we can assume they're in the same ratio. And you can also assume that that 10 is equivalent to the 20. We have to make a whole load of assumptions. If we increase the nitric by 50% and you increase the solution of sodium hydroxide by 50%, look what happens to the total. The volume has also, the total volume of the first reaction was 30. The total volume of the second reaction is 45. It's gone up by 50%, which means you have to heat 50% more fluid. And you've also got 50% more reactants, which means the delta T is exactly the same. It's really clever. The other numbers that the maths that people were trying to do. Can I just point out, most people got it right. Really, really impressed. Hold on, guys. How many moles of ions are present in barium hydroxide? Right. So number of moles is C times V over 1,000. So 0.025 times by 30 over 1,000 gives you the number of moles of barium hydroxide in total. Now, we also know that there's one barium 2 plus and 2 OH minuses. So multiply that by 3, you get the total number of ions. We're done. Clever, though. True. You were true, but I want to have Mr. Duncan as my adopted father. Oh, God. Olivia! Ugh. Next! I know, yeah. No, but I quite like the fact that it's Dunking. I quite like that. I am a king. Except the fact that I can't do my parts per million calculations at this time of night. Right, next, number 17. When 1.27 grams of copper is added to excess silver nitrate, 4.316 grams of silver forms. The Ionic equation is the top one. So you've added copper solid. We know silver nitrate has spectator ions, which is the nitrate ion never does anything. So there's 2 silver 1 pluses are going to go to the copper. You can split it into its halves if you like, folks. Copper's being oxidized, silver's being reduced, and you're forming silver metal. So it's the top one. The other ones, I think, right, can't be B, Ag is a 1 plus. Can't be C, Ag is a 1 plus. Can't be D, copper's going to form a 2 plus. We're done. Jog on. Nah. Next. By the way, some people might argue with me here and go, but copper can form a 1+. I can't even do that voice at this time of night. Copper can form 1+. Very, very, very unusual. It's a rarity, copper 1. Copper 2 is the most common stable ion, so always aim for copper 2. The process with the highest atom economy is the production of propene by cracking of icosane. That's going to be low because icosane is massive and propane is tiny, lots of waste. So low atom economy. 1 chloropropane from propane and chlorine, free radical substitution. It's going to be an absolute mess, low atom economy.
So we just need
to assume it's copper 2. Yes, David, that's absolutely right. By the way, who's Team OC? I really want to call you Timok. Yes, if you don't know silver's a 1+, you are stuffed. That is absolutely correct. I did actually give you at the start of the year, even though I wasn't teaching you calculations, I did teach you the ions, and an Ag 1+ was on it. Hi, Robin. Okay, next, cyclohexene by reforming hexane. Ugh. Right, so we're cracking hexane and reforming it. Yeah, that's not going to be a good one. You're going to have hydrogen produced as a byproduct, waste. Oh, the bottom one was a winner by a mile. There's no waste when you make a plastic, folks. There's no byproduct. They all bond together. NO3 is 1-. That's correct, David. Yeah, nitrate ions, NO3 1-. Oh, hexane, it's an alkane, folks. It's flammable. Know your symbols. D is toxic. C is corrosive. That goes with acids and alkalis. B is an oxidizing agent. That would go with potassium dichromate. That's what that, or potassium permanganate. Free radical, should have drawn this one out for you, folks. It was A. The reason being is oxygen has 6 electrons in its outer shell. If you form 1 covalent bond with a hydrogen, there's 1 electron left on its own. That's really tricky. You have to draw those out. By the way, the bottom one's C's water, so it can't be that. D's the hydronium ion, H3O+, which has got a dative bond. And B is an anion, the OH- sign, which means it's gained an electron from a sodium, which means it's going to have a full outer shell. So the answer is A. Tricky, though. Right, on to section B. Right, I've written in my... By the way, I did this at 6:30 this evening, so excuse my handwriting, it's a little bit messy. Right, lots of people missed that this was worth 3 marks. So there were 3 points. Number 1, it's giving you density. What that means is when you add the bromine water to the cyclohexane, the bromine water is going to drop to the bottom and the cyclohexene is going to float on top. So that's the first observation. Before shaking, orange color. After shaking, colorless, 3 marks. I even thought I'd draw a picture. So you've got the orange bromine water at the bottom with a floaty cyclohexane on top. And then afterwards, the bottom part of the solution becomes colorless. Draw the skeletal product of the major product, the major organic product of the reaction. And that's that one. Right, guys, you notice you do not get Br2. This is only with elemental bromine. We are using bromine water. By the way, I will show you that mechanism next lesson and show you how that happens. It's a beautiful mechanism. Has all kinds of lovely stuff. It's got electrophilic addition followed by nucleophilic substitution. So, nucleophilic addition followed with proton extraction. That's a delicious mechanism. So I'm happy to go through that with you next time. But yeah, you get that one with water. You always get an OH attached. Not that one. Elemental bromine, that one. With bromine water, that one. Next. Guys, this was hard. You've just got to know it. If you take an ene and react it with potassium manganate 7, you'll form a diol. And then naming it, by the way, they allowed it without the E. Fuming. Not happy about that. You must include the E there. Cyclohexane 1,2-diol. And the E is to separate the N and the D. That's the most common thing that's forgotten. Please don't forget. It is correct. Right, this one I've tried to explain a bit in a diagram, because I think there was only 2 people who got this, maybe even 1. Why are you guys talking about tofu fish?
Tofu dinner, because David got it right.
Laugh. LMAO vegan dinners. So that's just, yeah. Right, I tried to explain this because, guys, cyclos make no difference. You learned at GCSE that what happens is when you have your double bond, it breaks out. What? The double bond breaks open and they string together. So I then drew it as displayed without the H's, but then obviously then had to translate that down into the skeletal. That was tricky, that. Square brackets N. So this was your monomer. Double bond breaks open and they string together. That's the string. And then converted into skeletal and you're done. Not easy. But don't let cyclics freak you out. They do the same thing everything else does. Don't let it bother you. Next, we are going to add zinc to sulfuric acid. You're going to see it fizz. The proper word's effervescence. But fizzing, or bubbles being produced, do not say you make a gas. It's going to fizz. Why? Metal plus acid, salt and hydrogen. MASH. Taught you guys that. Zinc metal will reduce in size. Some will dissolve. Do you notice, by the way, it's excess zinc. So technically, year 12, if you put the zinc disappears, you'd get it wrong. I think they actually allowed it, which really annoyed me. But the reason being is it's in excess, so it will just reduce. You'll have less of it at the end. Some will dissolve. Ionic equation. Acid is, remember, any acid is H plus in an ionic equation. Sulfate makes no difference. And zinc always forms a 2 plus. You've just got to know it. Always a 2 plus, and then you form hydrogen gas. Remember as well, guys, conservation of electric charge. 2 pluses on this side and must have 2 pluses on that side. Right, this one I tried to bullet point out all the parts. When reaction is complete, the solution of zinc sulfate is formed. Some unreacted zinc is left. Describe how pure crystals of hydrated zinc sulfate may be obtained from the mixture. Filter out excess zinc metal, evaporate to reduce water content, evaporate 80% of the water off, allow to cool and crystals to form, filter out, wash with acetone, leave to dry in an oven. Actually, I've suddenly changed my mind. I would have lost that last mark. If you dry in an oven, you won't form hydrated. So just leave to dry on windowsill. That'll be fine. You don't want to put it anywhere warm. Oh, Sophia's joined the conversation. Hi, Sophia. It's nice to have you. 8 people watching. Cool. Guys, this is GCSE, working out molar masses. You can see how I've done it. Zinc 63.5, sulfur 32.1. I've done a little sneaky trick of 7 times 18. I know that water's 18. I lost the oven mark. Oh, yeah, you're not allowed the oven. I lost it too. Stop. Are you talking about tempura? Sup, Ritaj? Sup. Oh my God, I'm so not cool enough to pull that off. Calculate the number of moles. So yeah, guys, knowing MRs of water, carbon dioxide are always useful. It's worthwhile knowing those ones. 7 times 18 makes it quicker. Calculate the number of moles of sulfuric acid in C times V. Everyone got that. That was an absolute doddle. But then this one was quite tricky. Right, you can see how I've done it. First thing I had to do is I had to write out an equation. Zinc plus sulfuric acid goes to zinc, sulfate, and hydrogen. It's in a 1-to-1. So what's this say now? Whoa, chat blowing up. Just like Syria. Olivia, that's not. Oh no.
Olivia, that was
Syria. Oh, and no, don't quote Susan Boyle sings Nelly the Elephant. You know that's. Let's stick with that acronym, shall we, Olivia? Let's ignore the other one I taught you. So 0.2 moles of sulfuric acid also equals 0.2 moles of zinc sulfate. So how much should I have got theoretically? 0.2 moles multiplied by the zinc sulfate's MR, which gave you 5.712 grams. You did that from the previous question. You then did yield equals actual over theoretical times 100. They said he got 4 grams. He was meant to get that. Times 100 gave us 70%. So many people. Guys, sticks to your brain. It says 2 significant figures. So stop giving me 70.4 or something. Ah! Human. Next. Same functional group. Physical properties increase in a trend. I'll also accept similar. Similar, not same. Similar chemical properties. Lots of people lost it with same chemical properties. No, similar. It wasn't. It was over. It was like 70.4. Hair. I've lost my mind today, guys. What time is it? It's 8 o'clock, and you're making me do this. Hope you appreciate this. Structural isomers, molecules with the same molecular form, a different structural formula. Just learn your definitions, folks. Explain why butane can form structural, but propane can't. Butane can form... And I got the question wrong. Amazing. Explanation. Butane can form an isomer with a branch. Methyl propane. Propane has not got enough carbon. Whoop, whoop. Complete combustion. GCSE. I'm not going to go through that with you guys. Complete combustion. Oh, complete combustion is CO2 and water. And balance it as such. You don't.
Olivia's put, but you wanted to do this
late so people didn't have excuses. It's so true, and I've still only got 8 people watching, and there's like 16 people in the year group. I'm fuming. But it doesn't matter. As long as you guys are here, it's all that matters. Right, calculate the number of moles of propane. Who forgot to convert kilograms to grams? The equation is grams over rams. There's a reason why I teach that and not mass over MR. Because people will put in kilograms and not realize it. It's grams over rams, folks. Don't do anything else. So your first mark was converting 80 kilograms into 80,000 grams. Then dividing by 44 the MR of propane to get 1,818 moles. Next, right. It then said in the question that if you burn propane, it gives off 2,220 kilojoules per mole. It then said work it out in joules from 80 kilograms. So you take your moles, you times it by 2,220, you got 4 million something. Then that's in kilojoules. So then times it by 1,000 to put it into joules, and you're done. Next, it then says burners. By the way, this was my favorite question on the whole paper. I have never seen them do this. Loved it. It said the burner has a maximum power rating of 4,800 watts, and 1 watt is equal to 1 joule per second. So how many maximum amount of hours that a balloon would last for? Right. First thing, guys, to say, common sense. Who put that it was going to last 0.23 hours? Because, guys, that's like 15 minutes. How long do you think a balloon ride's going to be? Like, seriously, they've got to spend all that time filling the balloon with hot air. If you only had 15 minutes of fuel, you'd get 60 feet off the ground, and then you'd come crashing back down in a mess. Oh, crazy answers. So what you had to do is take that massive number of joules and divide it by 4,800. The reason being is 1 watt equals that many joules. You've just worked out how many the total numbers of joules in that much fuel. So you can work out how many seconds, because the wattage is in joules per second, that the fuel would last for. Divide that by 60 to put it into minutes, divided by 60 again, and you got 234 hours. Oh,
easy, guys.
It was my favorite question because it was like, I've never seen them give watts in joules per second before. I thought it was boss. I know, Raj, you can't get 17 million hours. Like, Raj, David Kim got 0.23 hours. Oh my, like, guys, Ritaj, apparently, hang on a minute, where is my calculator? Whoa, whoa, whoa. Someone divide, can you do 17 million, another 3, and then another 3, and then another one, another 0, one more. Right, divide that by, like you said, hours by 24 equals, right, divide that, that's days, divide that by 365. No, 365. 365. Oh no, what's that comma there? Divided by 365 equals. Ritaj, you then said that that fuel was going to last you 194,000 years.
I didn't, I got it right.
That's hilarious. Love it, Ritaj. That was amazing. That's made my day, that's proper brilliant. Right, next. This was the hardest question on the paper. No one, like, so few people got it. And do you know what, guys? It's not your fault. It says suggest. This, just like you are in real life. Right. Butane requires more oxygen to burn completely at high altitude. Would not, damn it, I've just lost the mark. Would not produce enough energy. Higher boiling point, melting point, it could liquefy, solidify at high altitude due to low temperatures. That was really hard. There were loads of other answers, but those are the two they wanted. The key thing, guys, if you've got a longer chain, you need more oxygen to get complete combustion. If you've got a longer chain, you're going to have a higher melting point, which means you're probably going to solidify or liquefy or do something. Clever question, though. I liked it. Right, this one was horrible. I thought it was really, really clever. Never seen them done it like this before. They take butane and they smash it. So you notice I've given the first equation. I'm explaining the atomization of butane. And it said if you smash every bond, then you're going to get that, and it's going to cost you that much energy. They then told you how much the carbon-hydrogen bonds would be. So I drew it out in a little timeline. Timeline, wrong word. Chemical line. If you take this molecule and you smash the CH bonds, you can see that I've broken all of these here. That would be 10 times 412.3. And that adds up to 412, times 0.3 times 10, 4,123. But it then said, so how much would it then be to break the last 3 bonds? Well, if the total line to smash everything was 5,173.3, you can minus out the carbon-hydrogen bonds, and you had leftover energy, which was 1,050.3. You divide that by the 3 bonds you're breaking. Each bond. Did I skip one? No, I didn't. Did I? Oh, I have. Oh, guys, I'm sorry. My photographs have failed. Which question have I skipped? Oh, no. What page have I gone from and to? 18. And that one was, I've missed page 16. Hang on a sec, folks. 17. Oh, nuts. Maybe it's somewhere else. Let's have a quick scroll down. There it is. There's 17. By the way, guys, you're going to laugh at me. I've got it wrong. This is what happens when you're doing things under pressure. Hess cycle. Yeah, guys, I've got it wrong. Look at my answer. The answer is actually 3995 or something. I got it wrong. And the tricky bit, the bit that I've got wrong is this bit. Plus 218 times 4. It was actually meant to be times 8 because look, it's atomization of hydrogen and they've got half H2 and there's 4 here. So that was meant to be times 8. Yes, David, I am human. I know that you guys think I'm not, but considering I can't do parts per million calculations and I've just made a mistake between atomization and bond dissociation, you can forgive me. Exams, Ritaj, you're absolutely right. It's exam panic. I was doing this while I was waiting for a pizza. That's what I was doing. And so I just spun through the questions. I was doing this in my head, by the way, as well. But yes, I did make a mistake. That should have been times 8. By the way, the cycle is the bit of actual importance. You can see what I've done. I've taken the data and I've put it onto the cycle. So the first thing it said was the enthalpy of formation of propane. So I can lob on that one from its elements to the compound. Then they'd even missed out an arrow. The graphite gets smashed into 3 carbons. The hydrogen needs to get smashed. Stephen Hawking did everything in his head. It's too soon to be making Stephen Hawking jokes, so I'm not going to. 218 times 8. Oops. And then that one's the question mark. You can see my overall arrow for their cycle. That way, from here to here equals from here to there. This one's against me. These two are with me. So if you then times it by the correct number, you'll get it right. Next. Right. 24. So you just had to fill in the table. They're isotopes. Same number of protons and electrons, different numbers of neutrons. And they actually just 20 and 22. Nice, easy 2 marks. Right. I went over this with Sophia today at the very end of school. If it says in a question, if it says use the information in the table, you've got to pull out data. And there was a mark for the data. This one had 20, this one, same number of protons, different neutron number. Quote the data. Next, oh, my beautiful mass spec. I did this with you guys. I am so proud of you, year 12. So many of you got this right. I was chuffed to bits. Sophia, are you saying you're sleepy? Why are you saying snooze? Am I that boring, Sophia? I'm sorry. Yes, it's 10 past 8 and I'm tired as well. So you can see how I've done the calculation. 39 times x. Some of you forgot and put in x and y. If you have 2 unknowns, you can't solve it, mathematicians. You guys can't even do it. So what you have to do is you have to do x and then 100 minus x because it's a percentage. You reorganize and you get a value for x, which is 95. So that's 95% of the 1's 5. It's the sound effect. Oh, see. I use simultaneous equations, x and y. I got it. Did you solve that through simultaneous? How long did that take you, Olivia? I could have beaten you in. I did that in like. You don't even need a calculator to do that. I don't get it. Robin doesn't get it. Right. Okay. Right, Robin. Do you know when we do this calculation, usually you have 39 times its percentage. And what's the second equation? Oh, I've just reorganized. Look, I've brought the 100 up. First thing is bid mass or bod mass. Hang on, bid mass. Divide, bid, hang on, bid. Bod mass. Brackets, indices. Divide, multiply. I don't know what the next one is. So divides first. So you bring the 100 up to through 39.1 times 100. You move the 100 off the left-hand side of the equation, which gives me 3,910. That will equal, look, expand the brackets. 39 times x becomes 39x. 41 times 100 is 4,100. 41 times minus x gives me minus 41x. So I'm doing the little expanding inside the brackets thingamabob that you mathematicians do all the time. So add and subtract. Thanks, David. So I get that. Then I rearranged it. I brought the 4,100 over to this side, so I minused it. And that would then equal 39x minus 41x. That then equals minus 190 equals minus 2x. Divided by 2 to get 1x, and I got 95. Well, that would have been 9 minus 95, but you flip both sides because that would have been minus x equals minus 95. And then you flip both sides. Oh, I hate all you mathematicians. Actually distributed across brackets. Distribute. Actual. Sophia. Oh, Sophia, why the crying face? Did you get that one wrong? Oh, actual distributing across brackets. I forgot the brackets. Oh, so close. Stupid brackets. Next, this question, year 12, fuming. This was a disaster. Number one, partly my fault. By the way, it was partly my fault because I actually explained to you, I have never seen them ask this. I've never seen them, ask you to translate out of logs. So I never showed you how to do it. I'm a chemistry teacher who's still learning. I need to spend more time with papers. It's ridiculous. So log IE equals 2.2. So therefore, the anti-log, so you bring the log both sides, which is anti-log both sides, gives you anti-log to the 2.2, which gives you the ionization energy. When you run those, you get those horrible numbers when you pull off the numbers off the graph. So you just had to run the numbers through, and it was a calculator job. Guys, shift log on the calculator. I know, Sophia, I know you just put 2.6. This is an A-level paper. If it was just read off a graph, you'd be in year 7. They wanted you to log it. It's not your fault. It's tricky that. If you didn't know the anti-log, then you couldn't do it. And I've never shown it to you. It's a geeky maths question. RAP, non-math students. I disagree. No, I disagree. Oh, actually, yeah, there was but Hess cycles, they're going to be there. They are. And I've shown you how to do that and the mass spec one with unknowns. I've told you that, taught it you. What? Wait, shift log works? Yes, it does, David. Of course it does. Put shift log and then just type in the number and it'll spit it back out. It's normal maths, though. Yes, Olivia, you're absolutely right. It's normal maths, not geeky maths. I agree. Right, why can't you plot it on a graph? I did tell you this, folks. The range is too large. You'd be trying to plot 300 and 390,000. So you minus the first ionization energy from the 19th. Robin, why would you do that? They're asking you for 2 values. Calculate the first and the 19th. I don't understand why you want to be minus them. They've asked you for 2 of them. Estimate the first one and the 19th, 2 values. And I did 2.6 and 5.6. So anti-log 2.6, there's your answer. Anti-log 5.6, there's your answer. Right. Write an equation for the first ionization energy. Sophia, you got it backwards, but you got 1 for the balance and the state symbols. So gas potassium plus 1 electron. You're done. Right, explain why there is a general trend in the value of the successive ionization energies. As more electrons are removed, charge on the cation increases. Don't put charge on the atom. Size of the cation also decreases. And remaining electrons feel greater electrostatic attraction to the nucleus. More energy to remove. I just gave everything. That's like 4 marks I did there. Only need 2. Right, this one's the only one that I really need to go through because this was a disaster. First thing I did was I wrote down the electron configuration. Gas symbols. Yes. David Kim. Jeremy Craig cries from his holiday home in Singapore. I have no idea what that means. RIP. RTFQ. Yeah. Read the full question. Ugh. So anyway, this one's the only one I really care about. So we needed to explain all 3 jumps, and each one was worth a mark. So what I did was I wrote out the electron configuration for potassium, and I looked at where the jumps were. Jump from IE1 to IE2, removing electron from the 4s, then the 3p. Less shielding, close to the nucleus. More energy. Big jump. Jump from IE9 to IE10, removing from 3s, then from 2p. Less shielding, close to the nucleus. Jump from IE17 to 18, removing from the 2s, dropping to the 1s. Less shielding. And we're done. Next, draw a dot and cross diagram for potassium chloride. And most people did that really well. Some people remember dot and cross. There were dots there, don't put all crosses. I wrote that the spikes were due to loss of shells. Is this incorrect?
Is this correct?
Oh, is this correct? Sophia, it is correct, but that's not enough detail at A level. The whole point of that question was for you to identify for each one where the electrons were being removed from, and you had to wind it backwards. Does that make sense? You had to state 4s to 3p, 3s to 2p, 2s to 1s. That was the mark for each one. 3 marks. Consider 3 marks. You can't just write down for each for the 3. You lost a shell, you lost a shell, you lost a shell. It's not, this is A level. Like you need to say more than that. You needed to say the locations. Hard though. Is this correct? I put that in my answer. Oh, actually, Sophia, I do remember your answers, and I did wonder whether or not you were before describing. Show me it tomorrow. I might have a look. There were lots of people who'd put all kinds of funky letters and numbers all over the place and saying lots of funky stuff. So I'm happy to have a look at that with you. Yeah, I do vaguely remember your answer and thinking that I don't know. We'll have a look tomorrow. We'll find. Bod marks. No, they won't give them. In fact, they flipped it, David. It's now, rather than benefited the doubt marks, it's now taken away if there's any doubt. They've actually reversed it, so watch it. Right, this was a disaster. I don't know why such a mess was made on this. Compare the electrical conductivity of a metal and an ionic salt. You say potassium metal conducts when solid, liquid, and gas. It always conducts. Potassium chloride conducts when liquid but not a solid. That was it. Next, describe 2 similarities in the structure and bonding of potassium metal and potassium chloride. I thought that was genius. They've both got cations in their structures, and they both have giant lattice structures.
Mr. Dave, does atom size matter?
Does atom size matter? You're saying it's going to get smaller. You should include details. It's in the question, Sophia.
Sorry.
I mean ion size. Yeah, I got what you meant. You should, but look at the question. Explain each of the 3 rises in the graph. You should include details of subshells from which the electron is removed at each sharp rise. For the 3 marks, you needed to say 4s, 3p, 3s, 2p, 2s, 1s. Those were your 3.
David.
If I wrote both cations were compared potassium chloride. Do I get a mark if I wrote both cations but compared potassium? Oh, David, that was hilarious. You just wrote potassium chloride and potassium chloride. No, I can't give you it. That was hilarious. That was really funny. Oh, I mean when drawing K and potassium. No, when Cl, sorry, does size matter? No, it makes no difference whatsoever. The Cl's fat and the K's tiny. But it makes no difference. You can make them all equal size, it makes no difference. Next, give 1 difference between the structure of potassium metal and potassium chloride. K has got delocalized electrons, KCl does not. Or alternatively, KCl is a lattice of positive and negative ions, whereas potassium metal is a lattice of cations with a CO delocalized electrons. And I think that's the end of the paper, folks. Oh, we're done. Let's go back to Hangouts. Let's go. I want to, how do I stop sharing screen? Stop. Way, we're back. Hey guys, I hope it was okay. I know it's been a long evening. It's 8:30. We've actually done that in about 53 minutes. So we managed to get through it pretty quick. I'll see you guys tomorrow if you've got any further questions. I'll sort out the parts per million question and those 3 multiple choice. But otherwise, have a nice rest of your evening, folks. Get a good night's rest, and I'll see you all in the morning. See you guys. Bye.